Okay, good afternoon. In this afternoon session, we have the talk of Kelvin Welsh, which is his master defense also. The committee is composed by myself, which I am the advisor, Aldo Procati from Federal University of Minas Gerais, and Pierre Pico from Marseille. So thank you for being part of the committee, and you have 50 minutes.
Thank you, Rodrigo. So my thesis has actually two parts. In the first one, we are concerned about the cluster expansion of the classical Ising model with long-range interactions. And we have new results. In the second part, it's actually a review of some papers about the extension of the probability theory for quantum systems. So since only the first part has new results, we chose to present only the first part, but I would be happy to answer any questions you may have about the second part as well. So some preliminaries. We define the long-range Ising model. So given any finite subset of ZD, lambda, and some configuration that must be defined on the whole ZD, we define the Hamiltonian, which is very similar to the usual Ising model. The only difference is this JXY, which in the usual Ising model it's a constant and it's non-zero except for nearest neighbor. But now this quantity here depends on x and y, actually on the distance between them, and it's never zero. Okay, for distinct points. So actually, this is the explicit expression of JXY, and we have this polynomial decay, which depends on the power alpha. And in order for the interaction to be regular, we ask alpha to be greater than d, where this is the dimension of the lattice. So it's a sufficient condition for the pressure to be well defined. Now we define the partition function as usual. So it's a summation over the configurations of the exponential of minus beta times the Hamiltonian. Beta is the inverse temperature, so 1 over the temperature. And we can define this quantity here, which is called the free energy or the pressure. It's well defined, as I said. And so the whole purpose of the work is to expand this quantity as a series, a convergent series, defined in terms of contours. But so we need to define the contours, and we will do this following the work of the talk of Lucas yesterday. But before so, I will talk a little about the history of the model and the problem. Actually, I will focus mainly in the cluster expansion, which is exactly the convergent series in terms of the contours. The model itself, long-range Ising model, has a very rich story, and I think Afonso gave a very nice lecture yesterday about this topic. Okay, so some previous results. The first major contribution for the long-range systems is this work here by Ginibri, Grossman, and Ruel in 1966. They worked on lattice cases. The contours are the usual Paris contours, so they are defined in the dual lattice. And in order to arrive at the results, they had to assume that alpha must be greater than d plus 1. So there's missing the region between d and d plus 1. Then Park in 1988, he proved the convergence of the cluster expansion for much more general systems. So any system that is treatable by the probability theory, so finite state space, Paris condition, things like that. and he used the usual Pirogov contours. So the contours in the actual lattice, right? But connected, the the the, the usual stuff. And he had to pay the price that alpha should be greater than 3D plus 1. Um, a nice exception of this kind of stuff is this work of 2014 by Cassandro, Merola, Pico, and Rosikov. It's a work in one dimension, but they used contours that were not connected, and they did manage to achieve the region below d plus 1. So in this case, equals to 1, so d plus 1 is 2. And he proved the convergence for alpha below d plus 1, right? So it's a great innovation. And I must say that our work is heavily inspired by this paper here. Okay, so now let's talk about the contours. As I said, Lucas already talked about the contours, but I chose to also give some recall in order to keep things clear in mind. So as usual, we start with the definition of incorrect points. So given a configuration sigma, a point x is called incorrect if there is some distinct spin from sigma at x in some neighborhood of x. In our case, the neighborhood is the ball of centered in x and radius 1. So for example, I have this picture here. This point here is correct because every neighborhood is also plus 1. But for example, this point here is incorrect because it's plus 1 and we have a neighborhood with minus 1. And also this is incorrect and so on and so forth. So if I paint the points that are incorrect, I get this picture here. And the set of all incorrect points is called the boundary of the configuration. It's usually denoted by the symbol. And the contours, as always, are the elements of some partition of the boundary of the configuration. Just a little comment. In the Pirogov-Sinai theory, the radius of the ball is actually important because the interaction is short range. So it's easy to see that if you take a large enough R, the contours do not interact with each other. But in our case, since the interaction is long range, we have no hope to have such a thing. So we can take R equals to 1 and it's as good as any other R. Okay, so in order to introduce the contours, I have to talk a little about the volume. Okay, so for example, suppose that it's some subset of ZD, right? Notice that we have some holes here inside. And the volume of this subset is just filling this hole. So this is the volume of this subset. So it's kind of the smallest simply connected set that contains the original one. Okay, now that we know this notion of volume, we can define the concept of an MA partition, which was defined in this here yet preprint of Lucas Afonso, Rodrigo Bissacô, and João Maia, 2023. So we fix some constants M and A greater than D. And given any finite subset of ZD, an MA partition is a partition, obviously, but that satisfies this equation here. So the elements of the partition must be sufficiently far apart from each other. What does it mean to be far apart from each other? What does it mean to be far or near? Well, the scale of the distance is the volume itself of the elements. There's more than one partition for a subset. There may be more than one. So we will always take the finest partition. It's proven in this paper here that there always exists a finest partition. And well, the contours will be then pairs, where this first slot is some element of the MA partition, so it's a subset of ZD, and the second slot is just the configuration on that subset. So this gamma here are the elements of the finest MA partition of the boundary of the configuration. Okay, so one more definition that's important, and it's actually non-standard, is the definition that we have of external contours, right? So usually, this is the definition of an external contour, right? So contour is external if the support, its support does not intersect with any the volume of any other contour. But actually, if we take this definition, we have some problems. I'll talk about that later. So we need another definition which replaces the volume here by what we call the modified volume, or V tilde, which is the support and the minus interior. So what is the minus interior? Recall that we had some, we may have some holes here inside the A, but it's a well-known fact that since you are, that the boundaries of these holes have well-defined configurations, right? So, for example, this hole bound here is +1, this here can be -1, but it's constant across the boundary of the hole. So we can define, well, the holes are the interior, and the minus interior are the holes that have -1 in the boundary. The plus interior are the holes that have plus in the boundary. So for example, again, here we have plus interior. So notice that in the boundary have plus signs. So the modified volume is the support together with the minus interior. So, for example, I have this picture. This gray area here is a contour, which I called gamma 1. So it's a set of incorrect points. Notice that we may have a non-connected subset. So this part here is also in gamma 1. And we have two other contours, gamma 2 and gamma 3, and a plus interior and a minus interior. So usually here we have one external contour, which is this whole gray area, this whole gray here, and two contours that are not external. So this and that. But in our definition, here we have only one contour that are not external. Here are external, right? Only these contour that are inside the minus interior that is not external, and this will be important later. I remark that although the contours in one dimension are very different by nature, they are in the dual lattice or triangles and so on. If you make an analogy, in one dimension, the notion of external contour is exactly this new one here. It's not the older one. Okay, so now we can write system as in terms of the contours. So we struck the ground state, and we can write the energy, the Hamiltonian of the system in terms of what I call one-body potentials and two-body interactions, right? So each contour itself has an energy that it's her inner energy, but also a pair of contours interact with each other, so we have this phi2 here that accounts for this interaction. So the formulas for the phi1 and phi2 are given here, but it's very similar to the other cases, except for the fact that here we have the modified volume. So it's V tilde instead of V, but the deduction is really exactly the same as before. I noticed that the feature interaction is this nice form here, and its modulus can be bounded by this function, which I call the f of gamma and gamma prime. And it's 4 times the summation of gxy for x in V tilde of gamma and y in V tilde of gamma prime. So this summation here is kind of exactly the interaction between the two contours. Okay, finally we define the spin flip, which is this map here. So it's defined for external contours. So this gamma here is an external family of contours. And the role of this map is to erase the family B gamma here. So we are putting plus boundary conditions. So in the support of B gamma, we put +1. So it has the same spin as outside. So we effectively erased the contour. But it's not sufficient, because if we only put +1 in the support, then it will appear some correct points in the boundary between the support and the minus interior. So we must perform a spin flip in the minus interior. So we change the signs of the spins in the minus interior. And in the plus interior and outside the volume, we take the same spin as before. And the effective is exactly as I said, to erase the family gamma from sigma. So the set of incorrect points remains the same as before, except for the support of gamma, which now becomes correct points. So the partition function we must write in terms of polymer, the partition function of polymer system. So we write in terms of the contours, and well, we may split the summation here over summation over external contours in first place, and then in contours that are internal to the external ones. So this summation here, in terms of the internal contours, are usually called the crystallic partition function. It's kind of a conditional partition function, so we fix some contours external, then we sum over the internal ones. And we call that z of gamma e, so it's the crystallic partition function. And now we perform a trick that's found in this paper here by Cassandro, Merola, Pico, and Rosikov, which is to divide and multiply by the same thing twice. So we had this partition function, then we divide and multiply by the products of the crystallic partition functions of each external contour. So this partition function here has inside the interaction between the external contours. So we are in the long range situation. The external contours interact with each other. But this product here is exactly like if the contours do not interact. So it's like they are independent with each other. So we divide and multiply by the same thing, and then we do again by this other quantity here, which has this little mark above the gamma. I will explain what this means. But this ratio here, I call W. All right, so the partition function is written this way. And so this partition function with this little mark above the gamma is exactly as before. So we sum over the contours that are internal to gamma, but now we apply the spin flip, the tau map, to the contours. So we raise the external contour, right? Okay, now we can use the Mayer expansion. That's very well known. In the interacting term, I will not give all the details here, but we end up with this expression for this ratio, where this k here is given by this rather cumbersome formula, but we may note here the Mayer function, so as always, which is given by the exponential of the interacting term minus 1. And with this this k here and also w, we can write the partition function like this, which is almost the partition function of a polymer system. What is spoiling is this term here. It's like a partition function of the interior of gamma, actually the minus interior. So what we can actually do is to repeat this process. So we perform a recurrence, right? So we write this partition function similar to what we did here, and then we iterate the procedure. And after a recurrence, we get this proposition here. So the partition function is written as only a sum over polymers and the product of the activities, and the polymers must be compatible, right? So there is a compatibility condition between the polymers. And it's exactly the same compatibility condition as defined in the paper by Cassandra Merla, Pico, and Rosikov. So usually in the Pirogov-Sinai theory, as I said, the contours do not interact. So the contours themselves may be seen as the polymers of the system. But in our case, since the contours interact, we must see the polymers as families of contours. So we call a polymer a set of mutually external compatible contours. And in order for this formula here to hold, we need a specific compatibility condition. In the case of contours, it's very easy. So the contours are really disjoint or things like this. But in our case, we have to be more careful. So we say that two polymers are compatible if, so B gamma and B gamma prime. In first place, if every pair of contours are compatible, so they form an MA partition. Okay, it's the first thing we ask. And in second place, we need that in one case the volumes do not intersect, so they are disjoint, the polymers, but they may not be disjoint. In this case, we ask that one whole polymer is inside one only contour of the other polymer. So, for example, the whole volume of gamma prime is contained inside the volume of only one contour of gamma, right? So, and the other way around here, one of these two things must happen. So these are the compatibility condition. We write like this, and we denote the set of polymers with the calligraphy P. Okay, so we have this polymer partition function with activities given by these expressions. Now we need to prove the convergence of the classic expansion. So there are two main ingredients. We have to bound the activities of the polymers in first place, but they also need to bound the entropy, right? So the number of polymers that are incompatible with a given polymer and things like this. So I'll not prove, I'll not give the details, but I'll talk a little about how to give some bounds for the activities and the entropy in the next session. Okay, so in first place, we need to define this function here. So it's the summation of gxy for x inside lambda and y outside lambda. So it's like the interaction between the interior of lambda, the inside lambda and outside lambda. Okay, and now we have this proposition here, also by Afonso, Bissacco, and João Maia, which gives a lower bound for the energy of erasing one contour, right? So here we have contour gamma, which is external, and another family of contours, capital gamma. And then we erase the external contour gamma here. So it's why this tau map here is defined. And then by erasing this external contour gamma, the difference between the energies is lower bound by this very good estimate here. So it depends on the support of gamma. So it's the number of points in the support of gamma, plus this surface term in the minus interior and the support of gamma. These three quantities here I call the norm of the contour. And so recall that W is the ratio between the partition function of gamma, some external contour gamma, and also the partition function, but with the external contour raised. So it's not surprising that we can bound this term here by using this estimate for the difference between the energies. So it's very easy so far. Now we have to bound the interacting term, which is not so easy. So I recall that f of gamma and gamma prime is given by this expression. So it's a lemma that we proved in our work, that the summation of this function, so what is happening here? We have some external contour gamma. Actually, it may not be external, any contour gamma, and some other family, capital gamma, here, which they are compatible. And then we sum the interaction between them for every gamma prime side the family capital gamma. And we can bound this summation here by the f, so the surface term, of the modified volume of gamma. I thought it would be nice to give just a sketch of the proof of this lemma, because it's not so much difficult, and it gives much intuition about how the contours work. So for the sketch of the proof, we split this family capital gamma in two families, epsilon1 and epsilon2, using the volume, right? So in epsilon1, we have contours that are, the volume is bigger than the fixed contour. So if you recall the definition of an MA partition, when so the distance must be greater than the minimum of the volumes, something like this. So if we have contours that have volume bigger than gamma, so the minimum is given by gamma. So in some sense, we have a uniform distance for the other contours. They are uniformly bounded away from gamma. So they may have a big volume, they may be huge contours, but they are far away, so it's nice. The other case, these contours here, they are small, so the minimum is attained by them. So they can be very close to gamma, but they are small. So it's the conflict between these two things. So for the first, we split the summation into these two cases. And for the first case, as I said, all the contours in the first case are with a uniform distance far apart from gamma, given by this quantity. So I call the ceiling of this quantity R. And so this summation is we can perform the summation for any x, for any y that is far apart from x, right? And this summation here actually converges. We can perform an integral bound or any kind of stuff. So, well, it depends on the number of points that are in some sphere around x, but it's given by this bound here, which, well, it's not difficult to prove. So we end up with this bound for the summation, right? So it's some constant, some very ugly constant, but the important thing is that it's bound by the modified volume of gamma. So notice that it does not depend on the family capital gamma, right? We can choose any family capital gamma. We only need, the bound is given only by the volume of gamma. With this exponential here, 1 plus a over d plus 1 times d minus alpha. For the second case, it's a little bit more intricate. We split even further by the volume of the contours gamma prime. And now instead, so let me take a picture here. So we fix some x in the contour gamma. And so here we have gamma prime and gamma double prime. So here, so fixed some x, I needed to sum over w inside the support of gamma prime and gamma double prime. Instead of that, I will bound by the distance of x to the contours. So it will be bigger, then I can do this bound. It's exactly what I did here. Notice that instead of x and y, I took x and the distance between x and the contour. And now we must take the minimal path. So back to the picture. This red path and this yellow path are the minimal paths. So are the paths that attain the distance between x and the contour. And we also take neighborhoods around the contours. So back here, we take a minimal path, as I showed, and we take also this neighborhood. So the points of ZD that have a distance smaller than this quantity here. And then we can prove this inequality. So what is this? If I sum the interaction term between x and each of these points that are in the intersection between the minimal path and the neighborhood, it's bigger than the interaction term between x and the contour itself, right? Because they are near. They are inside the minimal path, so they are nearer. So if you sum the interaction between x and each one of these points, it's actually bigger than taking the interaction between x and the contour and multiplying by the number of points that we have here, right? So it's exactly what I did here. The 1 over the distance of x and gamma prime is smaller than 1 over the distance of x and y, where y is in the minimal path and the neighborhood. But since we may have more than 1 point here, we can multiply by this constant, which is the radius of the neighborhood. So combining this inequality with the inequality that we had, we end up with this estimate here. And now we can, instead of summing over some y, we can really sum over any y that it's outside the volume of gamma. So we end up with this interaction term. Actually, these steps here are, in my opinion, one of the most clever tricks in the first paper by Lucas Afonso, Rodrigo Bissacco, Eric Endo, and Satoshi Honda. It's a very clever trick. And so, but recall that we have split in the volumes m, right? So now we need to sum over the volumes. But so it's we sum this fraction here, which have a fixed this exponent, so it's exactly the zeta function, right? The zeta function of the exponent, which is a over d plus 1 minus 1. And given the value of a, it's not difficult to prove that this quantity here is actually smaller than 2, right? So this summation can be bounded by this constant, which have zeta function, but okay. And the interaction, the surface term of the modified volume of the gamma. So again, I remark that it depends only on gamma, not on the family. It's very important. So we can combine the two parts, right? This bound here and this one. But we may use a bound for f lambda, which is found in this paper by Afonso, Bissacco, and Doen Honda, that the surface term is bigger than the set here over 2 minus alpha over d. And very simple calculation, we know that this exponent is bigger than this, so we can actually bound that ugly volume, the ugly exponent by this term that is exactly equal the second case. So we prove the lemma like this, right? So we can bound the summation of the f's by something proportional to f modified volume. With this lemma, we can now prove this other one, which is exactly the bounds in the activities. But I want to make a very important remark. That's the following. If we had defined external contour as usual, as the standard, then here it would appear a volume, not a modified volume, and it will not work. Actually, we tried, but doesn't work. Because this part of the activity W is actually better how the bigger the contour is, the better is W. So notice that here we have an exponential of minus something that's like the size of the contour. So the bigger the contour is, the better is W. But K, it's the other way around. So the bigger is the contour, the bigger is K. So actually have this competition between K and W. But W depends only on the support, these two first terms, and the minus interior. While if we had defined the external contour as always, we would have volume. So we would have a plus interior that will not have any thing to compete with. So it will not be possible to bound. So it's why we define the external contour like that. Okay, so for the entropy, Lucas already talked yesterday. The number of contours of some size n, so n is the size of the support, that contains some point, for instance 0, it's exponentially bounded. So it's smaller than some exponential of some constant times the size. And actually, this is the only thing that we need. We can prove this other corollary here from the activities and the entropy, which is a sufficient condition for the convergence of the cluster expansion. And the rest is just standard arguments of trees. So cutting the leaves and things like this. And we end up with the main theorem. So the statement that the free energy of the system can be written for beta large enough as this series here, which converges. So it's the cluster expansion, where these phi here are the Ursel functions given by this well-known expression. So now the concluding remarks, given that we proved the convergence. Well, we also did the bounds on the decay of correlations. It will be presented on Thursday by Lucas. It also worked by me, myself, Lucas, Rodrigo Bissacco, João Maia, and João Rodrigues. Also, a work in progress. It's the POTS model that we are doing myself, Lucas Afonso, Rodrigo Bissacco, and Gilberto Faria. And also the Pergov-Sinai theory for long-range interactions, where alpha is bigger than d, is also something that it's very natural to research. So it's this. I'd like to thank you all for the attention, but I'd like to give special thanks to the other authors of the paper. So Lucas Afonso, Rodrigo Bissacco, João Maia, and João Rodrigues. Nothing here would be possible without you. And I really learned a lot about what it means to do research with you, both the sad moments and the happy moments. So thank you, and is it.
Thiago é malandro, chegou nas palmas aí. Okay, so let's start with the people from farthest, the more distance. Is you.
Okay, thank you very much for your talk. So I really appreciate the work you did, and we're very surprised that you are able to do such very nice work in such little time, so important. Also, I want to say that it's very important that you discover that it's better to work with a lot of people than alone by yourself. So continue working on this. Okay, but now with the more scientific question. Okay, so you make something which is the very important result, but there are other question that you can ask yourself when perhaps, I don't know if you know this part of the theory that concerns the Milos and Sinai theory. This means that a priori you ask the following question. You impose that it's like a canonical assumption. It means that you will impose that the average magnetization in your system is smaller than the spontaneous magnetization. You have a phase transition, you have a spontaneous magnetization, and in particular with the cluster expansion you can compute the directly. You say the m beta, the spontaneous magnetization, is equal to something. It is 1 minus, and you use the cluster expansion to describe what is the correction with respect to 1. Okay, okay, see, this, you know that. And so a priori, you want to ask yourself the following question, is that what's happened if instead of having the average magnetization, which is equal to the spontaneous magnetization as it should be in the plus phase, for example, and you ask what's happened if you take an empirical magnetization which is smaller. Okay, so the mean loss and scenario theory tell you that what's happened is that a priori you have to create a droplet inside the volume where you will put all the minus sign more or less there in the droplets. Okay, and my question is that do you think that is a good idea to study that for your future, or you say that, because you mentioned a lot of program about something that you want to do. You want to do the POTS model, you want to do, but also it could be nice to, I mean, to start making something different, because a priori when you do the mean loss scenario theory or the Dobrushin-Kotevsky and Schlossman theory, you get the shape of the droplet. So there is very nice and important result of the shape of the droplet. But a priori, what do you think about the effect of the long range on such a droplet? You have to imagine that you have a droplet somewhere. Okay, you have the case where the droplet is inside a system with the short range potential. You have a short range potential, and you have a droplet somewhere. Now, imagine that you have the same situation with a long range. Okay, what do you think about not the form of the shape of the droplet? No, this is too complicated. But the localization of the droplet physically. It's a question from physics. Because a priori I can tell you something. Okay, more. When you have a short range system, the droplet could be anywhere. Okay, a priori, you do not cost energy to change the position of the droplet. Mm-hmm. But a priori, if you have a long-range system, it costs. Okay, so what is your conjecture for the localization of the droplet in the case of long-range system?
I think should be
the easiest.
Far away from the boundary or the.
Yes.
Yes.
Okay. Should be the center.
Yes. Yes.
Okay. So this is my only question. So thank you.
Okay. First of all, I would like to say that this is the result in this master thesis. If I was an advisor, it would be not a master thesis but a doctoral thesis, because the result is very, very good. Including, I try myself to prove these things, but I didn't succeed, because for me it was too difficult. Probably because you one have to study very well the literature, like the paper by Pierre, San, Zurti, to understand how to organize the contour. In any case, I would like to say that the master thesis is very, very good. For me, it should be a doctoral thesis. Your presentation was very, very clear. I more or less understand all the philosophy of your work. I understand that this work started a long time ago, 2 years ago, 3 years ago. You know, I mean, I don't know how much time you took to this, but of course for the collaboration with many other guys, including all young guys. This is very important, because young guys can run much faster than old guys. And So, so congratulations, wonderful work. My question, I have two questions. I try to do this, but the philosophy that you follow is that you first construct the contour standard that you approximate contours with not correct contours. Once you have this, you collect and these polymers do not interact because in the beginning the contours interact in long range interaction. But then in the final, all the long range interaction is defined with that. But now the final solution, there is always only incompatibility
Condition.
they are at fault. They don't interact. Just and so you can apply the standard condition.
Mm-hmm.
Condition you can you have to bound the activity. You have to count how many polymers compatible with the polymers. This is the philosophy. Now, there is because you know the condition is that you need a polymer gas which is our core, but there is a generalization of the polymer gas in which polymer can interact via interaction which is not our core. Ah, sì. Ah, okay. Okay. There is a generalization of the abstract polymer gas in which polymers, well, not exactly the abstract polymer gas, the subset gas, which basically, in which polymers can interact through each other with an R core plus a long-range interaction. And there is a condition for the convergence of the cluster expansion for this gas. I wonder if it's possible to go in this direction also, to instead of constructing large cluster of polymers, using smaller polymers, just maybe connect and using this generalization, the cluster expansion for an abstract polymer gas. But this is a curiosity, not a question, because you were able to do the things in this manner. But I'm interested because also because this generalization of the abstract polymer gas was a paper of mine, so I have an interest. So this is a first question: if you consider this possibility at some point, or not? You just follow the ideas.
I saw that there is an extension of your work for I think it's called softcore.
Mm-hmm.
Is it what you're talking
No,
about?
it's not. Softcore.
Right.
There is an extension by SOCA. The interaction is softcore and mass positive, but there is also an extension where the interaction can be anything, also negative, positive. Well, there is this. So you didn't go in this. We didn't. One last question. In the final result, maybe you yes, the final result. Yes, the free energy of the system can be written for beta large enough, blah, blah, where and this is convergent, certo? And this is convergent. Beta large enough, you can say exactly, you can say what is this beta large enough. Beta is greater than something that depends on alpha. Because
yes,
this
yes.
what we were talking about this in exactly, but you have it. You have
Yes,
it.
yes,
you have a beta is something, but there is a beta. If I know alpha, if I know the
Actually, we were not so interested in this bound for bit, so we use I think the Kotes is
no, I'm not saying if the beta is optimal, no, because just to
yes,
find a beta
it
is
can be,
important.
okay.
But because we were talking about this philosophy during lunch, that Galavotti said that there exists a content for beta large number. Galavotti said, well, but how much? 2, 3, 20. So you have the exact value of beta. No? I'm not. It's not important at this point to see if this beta is optimal. Of course, in 30 years, 40 years, when these things will be clear, other students will try to improve the constant beta. So this is my. In any case, I just want to say one more time, congratulations for congratulations also for all the people that participate to this result, because I understand that it was a collective work with various people. No? Okay, thank you very much.
Okay, just before my comments, and but about the comment of Pierre, but if alpha is bigger than d+1, maybe the systems, even for the wolf shape, could be kind of short range, you know, if it's the case very fast. Because one of the things that we found this actually after Lucas talk, he mentioned that the d+1 is some kind of critical. Well, we had the proofs long time ago for d+1, and it was more or less easy with respect to what we are doing now. And so maybe this is one of the things. But okay, so let's. Okay. Well, yes. Very good. Yes, it is my just the true question, right? Okay, of course. Okay. So okay, let's do my comments. Okay, the presentation we knew it. We trained a couple of days, but we trained in some sense. He came. Everything was done. It's very good. And so, but maybe it's a good time to recover the history of Kelvin. So, and here at USP, as you can see, we have a lot of very strong students. This is fully of them. But surprisingly, it's not easy to find people to be the mentor for them. I have students with grades, I don't know, the score is 9.8, and they have difficult to find the advisor. So that's why I have a big group, because in some moment I decide to, okay, let's say okay, you have to spend some time, you know, with your group, so you have to do less other things, but as you can see, it makes sense. so in time ago, when Calvin came from the Physics Institute, and they tried, they were looking for someone to be the advisor, and I think I was the third option, or maybe fourth. Third. So I was not the. So at some moment they found me, and they say, okay, okay, give me your grades, and it was very good, and so I accepted him and João Rodrigues, which is there. And so we started. So okay, so we do this course, do this. So during the undergraduate studies, and he did a lot of things: ergo theory, functional analysis, probability. So he knows a lot of stuff. So this is only one small part what he knows. And then, okay, we applied for FAPESP, as you mentioned. Actually, FAPESP is maybe the main reason that I can do the things that I send the students for other countries. This is why we can do the things. So I send them to okay, go there and discuss with Yang Ding, for example. They visit China. Anyway, So okay, so Eddie, Kelvin did the undergraduate studies and physics, so he came to the master here in the with our group. So we had in the beginning this project of to study Pyrgov Sinai. Also, he read the paper of Zradnik, but he had no time to put in the test because at some moment, okay, so let's try to start the research. So I changed the project because Lucas was doing his thesis, and Lucas was in Canada, and after he come back to Brazil, and I was traveling to Poland during 1 year. So during this process, he stayed 1 year alone, let's say alone. That's why now it's important the group. So when I went to Poland, Lucas came back from Canada, and so I said, okay, let's do a different thing. Let's move, change the project, and let's start to do research. So since at this moment we had the contours. So and we start in the beginning because we discussed a lot of Arnaud Van Etter if the contours, even Arnaud tried to say no, maybe it's not right. We discussed a lot of until at some moment we found that okay, this is the right. Since you can see we can go until the critical exponent in all the works basically. So that's why we changed the project, and so the Kelvin started to do research with the other students. So I was in Poland, and they were working together, mainly with Lucas and with João, and after João entered in the project. So that's more or less the history of this paper. So that even so that he was not so confident about the dissertation that he stopped to work in the paper. So that's why we don't have the paper, because in one part of the project it was okay, let's teach this guy to write a paper. So that's but at some moment we didn't finish the paper, but the calculations we just don't have the final version. But it was more or less the history. We really believe in this kind of let's say is a collective process here. In general, it's me, some senior students, and never to be completely alone. This is more that's why we are so fast. So we are not never a student because since it's very hard. So if you go, I mean, it's impossible. So that's why. So congratulations, it's is very good. And now, of course, we have to write the paper. So I have to by official rules, I have to ask for everybody go out to decide. So, okay, after a long discussion, they asked me if it's possible to give, say, let's say you approve it with some more. So I said, no, that's unfortunately here we only have approve it or not. So you are of course approved. So congratulations.